begin with a presentation by myself and Lipen Wang with a project overview and some description of the work that led to this collaboration, followed by a short presentation by Qingchong Xu, which corresponds to a follow-up of previous collaborations between our two institutions. And then we will have four presentations, one by each member of the International Advisory Board. So Remco Julenhoyt, Alan Seed, Chandra Sekar, and finally Daniel Scherzer will share their some knowledge on this topic. Okay, so a few words on the context of this project. So there is an overall context where we expect an increase of rainfall extremes in the future due to climate change. And this has been further confirmed with the latest IPCC report. And this is done with high confidence. And also has shown in recent studies, rainfall has a negative impact on economic development. And the last point is that there is a growing proportion of population in urban areas, which will be of roughly 80% by 2050, according to UN forecasts. So to summarize basically this, people are living in cities and rainfall extremes, which are negative for economic development, are increasing because of climate change. And there are several challenges which are associated to stormwater management in urban areas, notably a high level of imperviousness, meaning that rainfall is becoming immediately a large proportion, significant proportion of rainfall is becoming immediately active in the runoff process. There is also a strong heterogeneity of the land cover, meaning that the distribution of land cover in cities is complex and should be accounted for, and meaning that it also requires to have modeling tools which are tailored to this complexity. And numerous studies, including some previous work that we did in previous project with Lipen, notably the Rain Gain project in Europe, showed that there is a strong impact of small-scale rainfall variability in urban areas, and there is a need for data at high resolution, typically of 100 meters in space and 1 minute in time. So in this framework, progress on the understanding, measuring, and modeling of rainfall in urban areas, as well as stormwater management in these kind of complex areas is much needed. And there are several features which should be accounted for when dealing with this issue, and notably the rainfall that should be understood not only as a simple rain rate, but also as a complete drop size distribution, exhibits some scale invariant features, multifractal features even. I will come back on this word later in the presentation. From drop scale to large scale, and that's an illustration at the drop scale that you can see, or an illustration of the variability of during a rainfall event of this drop size distribution. And some parameters can be the temporal evolution of some parameters. It's shown to exhibit some scale invariant features. And what I said for rainfall is also true for wind, which exhibit also some scale invariant multifractal features. And that is one basic consequences of this behavior is that, as we expect in this theoretical framework, there is no power law, there is, a power law tail for the probability distribution of the wind fluctuations, for example, which are displayed on the bottom left, where you can see, for example, the blue curve. At small scale, you have a clear departure from the Gaussian framework. So we have power law tails for the distribution of the values, and notably in this case of the fluctuation of the wind. So there is a need for an appropriate framework to handle these features. So to come back more precisely on the purpose of this project, it aims at improving the quality of radar quantitative precipitation estimates at high space-time resolution by addressing mainly two issues. The first one is accounting for DSD variability, and notably the one that is occurring below radar observation scale. So there will be some focus on this in the project. And the second one is better understanding and quantifying the wind drift effect. And this is illustrated with the picture on the bottom left that you can see, where you can see that basically the problem is that weather radars are measuring rainfall in altitude, typically at 1 kilometer or 1.5 kilometer, and hydrometeorologists are interested in rainfall at the ground level. And between the height measurement and the ground level, there can be wind advects the drops. And this can be result in complex features. So for example, on the picture that I was mentioning, there is a drift toward the right part on one side of the mountain and toward the left part of the rainfall on the other side of the mountain. So that you also need to account for the complexity of the wind field. And for this, dual approach will be implemented. There will be a coupling between rainfall and wind in the first place. And we will also work on tracking rainfall cells in 4D using 4D radar data. And in the second step, there will be a quantification of the impact of both aspects on stormwater management. So to summarize basically the content of the project, it's divided into four main work packages. One work package dedicated to measurement with a refinement of existing monitoring network in both Paris and Taipei. And then two work package dedicated to the two issues which I previously mentioned in the slide just before. And a fourth one, evaluating the impact of the findings of these two work packages on hydrological applications in urban areas, relying on case studies that we are studying for several years in both Paris and Taipei. And we will benefit from the expertise of an international advisory board, and they will, for example, share some insights on the topic in the next minutes of the meeting. So there is a team in ENPC, in the HM&Co laboratory, where there is Yulia Chigrinskaya, who will work on the topic, and myself, and we will hire one PhD, a postdoc, and a few interns. And similarly, in Taipei, Lipen will also hire a PhD and master students. So we will shortly circulate some sheets to hire these people. And so just to say a few words about the existing monitoring network in both cases. So this is what we have in Paris. There is notably a dual polarization X-band radar, which has been installed for several years, since 2015. That is operated on our campus. And on this radar platform, there is also 3D sonic anemometer and meteorological stations, and as well a dysdrometer. And we also have on the roof of the other roof of the building a network of dysdrometer, which is being installed with dysdrometer by several manufacturers. You can have here, there is a OTT Parsivel. We also have a PWS 100 by Campbell Scientific, and a 3D stereo by TIS, which has been installed 6 months ago. And in order to get information of the vertical variability of DSD, micro-rain radar, sorry, has been ordered and should be delivered shortly here. So that is an example of the data that is collected, and that is that's concerning the hydrometer and anemometer data on the right part. And some data can be accessed through the images of the data can be accessed through the links which are mentioned on the slide.
Yeah. So just a few words about, we also have a rain gauge network we install in on the roof building of our department building in Taipei. So you can see we have a network of 5. 3 of them are catching rain gauges, and 2 of them are a hydrometer and mini radar, and they are non-catching gauges. So that we can provide very high resolution rainfall record there from the finest one is from hydrometer, that's 10 seconds, and also others can provide 1 minute rainfall record. And also the spots, the network, the location we install this network, as I said, the rooftop is also, I'll say lucky or unlucky, it's in a hotspot of a thunderstorm in Taipei City. So at here, we've installed here for 3 years. We already collect several really extreme rainfall events here. And through this project, we're going to install similar to the network in Paris. We're going to install a 3D ultrasonic anemometer here. So sorry, next slide. Yeah, so we install this network for several purposes. One is we cross compare gauges that collect rainfall in different with different mechanisms here. We also use the data here to develop quality control and data processing algorithm, and also the data platform you can see in the left-hand side, because the high resolution data in 10 seconds, that's really a great amount of data. So we also develop the platform, and also here you can see a QR code. You can link to our GitHub. Actually, all our data are open. You're for free to use the example there to download data, and so to do some analysis by yourself. We also, a very special part is we also use this network as a test size, because we're also developing our own raindrop, low-cost raindrop sensor here. And finally, we also use it to observe some physical transition of rainfall process that we will present later in today's talk. Yeah.
Okay, thank you. So now we will briefly make 3 short focus on the previous work that led to this project in both our institution. So I will start with a preliminary study on where are drops falling in a turbulent wind field, where the idea is that rainfall is commonly it is commonly assumed that a raindrop falls vertically at a speed equal to its so-called terminal fall velocity. And in this investigation, the idea was to also work on the horizontal velocity of the drops falling into a multifractal turbulent wind field. So just to illustrate the interaction between drops and wind, these are just a short snapshot from a video taken from my living room, where I have the pleasure to see a lamppost. So when it rains, I can record rainfall with simply my phone, and the yellow arrow here are showing the horizontal direction of the drops, and you can see that there are, just over the course of 10 seconds, strong variations going in one way to the other and coming back. So that's just to illustrate the importance of accounting for the horizontal velocity of the drops when studying the trajectory of drops. So in order to study it much more precisely, we used an equation basically equating the acceleration of the drops to the 3 main forces, the 3 forces that are acting on it: the drag force, the buoyancy, and the gravity. The trickiest one to estimate is the drag force. So we developed an approach using shapes available in the literature for drops, accounting for the fact that they are becoming more and more oblates with increasing size, and formulas for computing drag coefficient for this kind of shape with an axis symmetry available in the literature. And then some numerical solving through an explicit scheme was implemented. So I will just say a few words on universal multifractals before going on, because it's going to be used in the next part of the study. So it is a mathematically robust, physically based theoretical framework enabling characterization and simulation of geophysical fields, which exhibit an extreme variability over a wide range of scales, such as rainfall or wind. And in this framework, the statistical moment, for example, of a given field are power law related with the resolution, that is the ratio between the outer scale and the observation scale of that we are studying. And the exponent quantifies the whole variability of the field. And for non-conservative field, you have to add an additional parameter, which is called a non-conservation parameter, and corresponds to a level of fractional integration that needs to be implemented. So in this framework, the whole variability can be quantified with only 3 exponents. So basically H, the degree of non-conservation, C1, the mean intermittency, and alpha, the multifractality index, which quantifies how fast the intermittency evolves when slightly going away from the average field. And interestingly, these parameters have very straightforward consequences on the extremes. If alpha and C1 are large, then you have strong extremes. Otherwise, you have only low extremes. So then if I use a wind input, a horizontal wind input corresponding to a multifractal field with known features, so it corresponds to the black curve, and then you look at the response of each drop during their fall, the horizontal velocity, at the other curves that are plotted for different size of drops. So for small drops with 0.1 millimeter, it's in blue, or larger drops, 0.6 millimeters in green, sorry, or 2 millimeters drop in red, you can see they behave differently. Small drops will follow with a slight time shift, more or less all the fluctuations of the wind, even the small scale fluctuations, whereas larger drops will dampen these fluctuations. And this can be quantified. So if we study the multifractal behavior of these velocities, an excellent multifractal behavior is found, with alpha and C1 remaining rather constant, depending on the size of the drop, whereas the parameter H is rapidly increasing for small drops before stabilizing. So basically, it means that the properties of the wind input and all the associated fluctuations are retrieved on drop velocities, simply with an increased level of H parameter. So in the second step of this study, the idea was to study the trajectory of drops in 3D. And this was done with a very simplistic reconstruction of a space-time wind using scaling laws and over a large area using scaling laws and anemometer data that was collected during the previous project. And some more complex ways of simulating wind will be discussed in the last presentation of the meeting. So using this kind of simulated wind, the trajectory of drops can be simulated. So that's an example from a drop falling from 1,500 meters down to the ground. And you can see the projection of the drops on one axis and the other in the background. And some complexity in these trajectories are observed and should be accounted for. So that's just an illustration using 30 drops, 10 drops from each size, sorry, 4 different sizes. And they are all starting within a cubic volume of 100 meters, roughly corresponding to a radar gate in a way, over a course of 30 seconds. And we wanted to see where they fall, basically. And you have a projection of the trajectories of the drop along the x-axis, the y-axis on the two first column. On the second column, the third column, sorry, you can see the spread of the drops at the ground level. And it's for one low wind event in the top, and in the bottom, it's for a strong wind event. And what can be noticed is a stronger shift for smaller drops because they spend more time in falling. So they are more affected by advection. There is also a decrease of the spread of the drops as the drop size increases. And last, which is the main topic of the talk, there is a shift of several radar pixels. So for example, if you look for the strong event, there is a shift of typically few kilometers in one direction and in both directions, which can strongly affect the estimates of rainfall, especially if you are interested in high resolution, which is the case in urban areas. So that was one of the studies that led to this project. So now I will let Lipen present other things.
Yeah, thank you, August. So we'll talk about the focus too. So basically, it is kind of highly related to the work package 3 of this project. So our focus is explore the potential of computer vision and machine learning techniques to model wind drift effect from 3D radar data. So here, just to show you just some very preliminary work we have done here. So now we are working on to develop optical flow-based algorithm. But instead of to track the movement of rainfall from two consecutive 2D radar, actually we're looking in the vertical direction. So we from there we try to estimate how rainfall move vertically along the vertical axis. Next slide, thank you. And relevant to this work, actually, myself and my team, we start to work on this kind of application of computer vision, such as optical flow technique, in one of our publication in 2015. So here I use it's the first time we start to use optical flow technique to generate high temporal resolution radar data. So we basically derive the movement from two consecutive radar data, and based on that, we can generate high resolution radar images. And then from the right-hand side, you can see it had the impact when we do hydraulical application. Next slide, thank you. Yeah, and also in addition to computer vision, we also have some experience to investigate the deep learning. It has been quite popular. So what we do here is there was a quite successful application of deep learning technique to radar-based rainfall nowcasting that's called DGMR. It basically is a nowcasting model developed by DeepMind company in the UK. So what we do here is we try to reproduce what DGMRs have been doing. So we replicate their model, which they didn't publish source code. So based on their publication, we replicate their model, and then we investigate the whole process, why their model is more successful than other deep learning model published before them. So we further confirm that actually it's very important in their model. They still account for the scalding behavior while modeling rainfall. So if you're interested in this model, it's open source here. So from this QR code, you can access our model, and then you can play around this model we replicate. Next slide. In addition to the field-based nowcasting or rainfall tracking, we also, because of the nature of convective storm, so we found that objective-based still tracking is more effective for convective storm nowcasting. So from here in 2018, myself with some researchers from KU Leuven, we developed an algorithm called Enhanced Titan. Basically, it's based on a very famous Titan algorithm to track the rainfall object. But here we did some modification, basically two modifications here. The first one is we introduce a multi-threshold algorithm. So if you look at the top left two images based on multi-threshold, we can separate RAN cell better, each RAN cell object better. And also a second modification we introduce here is we run the field tracking algorithm first. So this method can guide us the movement of the object, the rainfall object or rainfall cell. So from there, we can better associate a rainfall cell from two successive radar images that will indicate the right-hand side. And then in 2022, based on this algorithm, together with another nowcasting algorithm developed by Rosie in 2015, based on common filter. So incorporate our tracking together with this common filter method. So we develop a probabilistic convective storm position tracking nowcasting system for the UK Met Office. So basically, so here we can use our track result to further extend to predict the movement of each rainfall cells. Next slide, thank you. But the thing is, we also have some follow-up work because for convective cells, actually, in addition to the advection, it also had very strong evolution with time. That shouldn't be ignored when you try to predict the convective storm. So here we were inspired by you can see the upper left corner, were inspired by the observation of the physical process of the evolution of convective cell. You can see they illustrate here in 3D. So from here, we're inspired by, you can see there is a very strong core, that's a convective core that's will change throughout the life cycle of a convective cell. You can see the altitude of this core will raise first and then go down at different. It will change according to the life stage this convective cell is. So inspired by this, we further so in this recent work, we work with 3D radar data. From the 3D radar data, we extract this convective core altitude, this kind of feature, and then we incorporate into a deep learning method. It's a very standard LSTM model. We incorporate that into, and then we can quite well predict the evolution of this convective cell, how they evolve with time. With a single model, we can whether the RAN cell is in the developing or in the mature or dissipating stage, and this model can very well predict this. Okay, next slide. I think we move to the focus 3.
Okay, I will talk about the focus 3 that we have collected because we have a very high temporal resolution data collected in Taiwan. So we use this data to do some analysis on the typhoon events. So we select 3 events all in 2022. You can see the time series here. They range about 90 hours, but the one is shorter, so the 45 hours here. Next slide. Next slide. Thanks. Okay, so as we mentioned before, the tracing moment technique, and for universal multifactorial, we have the scaling moment function K of Q. But when we look at K of Q, you can see 2 types of multifactorial phase transitions. The first one is the sampling limitation, and the second one is the divergence of the moments. And the sampling limitation is related to the fact that the usually the gray moment cannot be observed because we have a very limited data point. But due to we have very high temporal resolution data, so now we have more than 30,000 data points for a single event. So this is a very rare case that we can do the analysis on the time series. And to put it simple, that when we want to understand the sampling limitation, we can understand that beyond a certain point, moment Q, that the statistical estimate of the scaling moment function becomes unreliable. So it's quite important for us to understand the analysis result is reliable or not. And the second one, the divergence of the moments, is related to the singular limit of the underlying cascade process. It means that when there's a very extreme intensity happens, it will set a limit for moment Q. And when we exceed the moment Q, that the moment will start to diverge. Yeah. And the next slide, thanks. Next one, yeah. So here is a very rare case that we observe from our data. Usually, the common case that usually we can think that we can observe that the limitation is controlled by the sampling limitation, like the upper one, the HM&Co in this case. But it's the kind of for our team is the first time we observe the real case that for nail gate that we can see that from the KFQ, this curve, we can observe the curve diverge from about Q equals to 3. And we also look at the critical moment, the divergence of moment, the critical moments. It's the first time we can see the matchup here. You get the QD is about 2.795. So it's quite a rare case. So this is this kind of discovery that we are going to want to publish in a journal later. Yeah, and this is quite important for us because when we want to do the downscaling process in the future, that we need these kind of techniques to help us to make sure that our parameters is reliable and we can choose the right parameter to do the downscaling. So we also have another work is going on to work on this to develop the strategy for the downscaling. Thank you.
Okay, thank you. Thank you. So we have time for a few questions. I saw that Chandra, you had a question. You can speak if you want.
Yeah, first of all, I want to apologize for joining in a few minutes late. It's a little too early here. Sorry.
It's a bit early for you.
I sent a message at 5:30 a.m. and but it's nice to see all of you. And I also am very happy to see some of my past work is referred here with Pekka Rossi. Pekka Rossi was my student. I also have an appointment at the University of Helsinki. So as part of that, I was working with him on that particular paper. The main thing I wanted to say was you were, this is to Dr. Wang, you were referring to the optical flow, and you were also referring to Titan and the object. These are fundamentally very different methods because this is based on object flow, and whereas the other one is based on precipitation as a whole field. And when I mixed the two things in the past, I got into trouble. So I just wanted to share that experience with you. That's all. But it's a side comment, so it's not very important. But hi. I also wanted to tell that I'm paying attention.
No, thank you. That's really useful comment. Yes, indeed. Currently, we don't really integrate these two methods yet. It's more like I use optical flow to kind of to do the first run. To do the first run to help me to know the general direction of the whole field, and then I use it as an initial guess to my object base, to my Titan method. So so in this case, my cell, the old my cell will try to move to a more similar direction instead of sometimes because of the tracking error, the algorithm error. So you may get something very funny. And also actually for forecaster work in the Met Office, they will prefer the smoother trajectory from the RAN cells. So that's,
I will send you. I'll send you a couple of recent papers I have in IEEE on the same topic when I get a chance. Maybe I'll get my email from Augusta and then I'll send it to you.
Perfect. That would be really helpful. Thank you.
Thank you.
Okay, yes, Remco, I can see you have a question.
Yeah, indeed. Thank you very much for your introduction to this interesting project. I was just wondering, is, let's say, the investigation of the effect of the observations on the retrieved physics a subject or topic within your project? For instance, when you say, okay, we can describe precipitation as a multifractal field, you observe that field using a disdrometer or a radar or any other instrument that would, observe this field at a particular scale, but also spatial scale, temporal scale, but of course also indirectly, because it typically employs electromagnetic scattering to observe what's going on. So that would obviously affect, I would say, the retrieved physical properties of the rainfall field. And I was just wondering, I'm sure you are aware of this, but is that, let's say, aspect of the problem part of the ongoing project? Thank you.
Yes, it will be part. And so some portions of the work, notably the PhD student who will work on the variability of the drop size distribution and its consequences, will definitely address this issue.
Yeah, it's just a quick word from my side, because in our case is we have gauges from different mechanisms there. So what we do here is we cross compare this measurement at, for example, now it's at 1 minute resolution. So at 1 minute resolution, we can try to observe the kind of cross compare to make sure the consistency between them. That's how we control the quality there. Then obvious, of course, disdrometer in 10 seconds, we don't have other measurement to be able to make sure that to guarantee the quality, but at least at 1 minute I cross compare and then make sure the consistency between them. So based on that assumption, we to see how much information we can retrieve on that. Thank you.
Okay, thank you very much.
Okay, thank you. So I believe we can move on to the next presenter, who is Remco, directly. So I will stop sharing my screen so you can share yours if you if you want for a presentation. Slightly less than 15 minutes, so we have time for 1 or 2 questions. Okay, yes, we can see your screen.
Need to unmute myself, otherwise presenting would not make much sense. Can you still see my screen, or?
Yes, we can.
And now?
Yes, we
Are
can
you
see
able
the
to see my screen, Auguste?
Yes, I am, but it's not in full screen.
Yeah, funnily, it is in full screen here on my side. So anyway, well, we'll do without if that is not a problem. If you're able to see a large part of it, that would be fine anyway.
Yes, it's fine, and I will let you know if the slides do not change.
Okay, excellent. Thank you very much. So yeah, I was asked to present some work here at the kickoff meeting of this interesting project. Wasn't quite aware of the audience I would get. Turns out there's quite a number of people here. This is just some work we did some time ago and actually still working on regarding the parameterization of drop size distributions and their variability, which I thought would be fitting for the topic of this kickoff meeting. Can you see my next slide, Auguste?
No.
Oh, that's interesting.
It's not the next one. We are still. Maybe you just share a window and not a screen. I believe.
That's interesting. Let me try and resolve this.
Yes.
Share. Well, first, I need to stop sharing, probably.
You are not sharing right now.
Okay. Share. Are you able to see the slide now?
Yes, we can see the first one.
Now the question, of course, is, are you able to see the second one?
Yes.
So we have the second slide now.
Yes, perfect.
Okay, that's great. Thanks for bearing with me. So basically, why would want to observe raindrop size distributions? Well, obviously, first of all, because of their intrinsic interest from a perspective of understanding the physics of precipitation. Secondly, for instance, because it's a crucial element in any retrieval algorithm for remote observations of precipitation, notably radar, satellite, but also, for instance, commercial microwave links, which is a subject we have been working on quite a bit lately. Now, scientists have been observing raindrop size distributions for well over a century. These are some images taken from a paper by Bentley from the early 20th century using the well-known flower method. Obviously, nowadays, and I must admit, this is already some time ago, an earlier version of today's presenter. But obviously today we're using impact disdrometers, we're using optical disdrometers, video disdrometers, and vertically pointing radars for that purpose. And other types of instruments have been developed to observe raindrop size distributions ever since. Now, typically what researchers in this field are doing is observing time series of raindrop size distributions, such as are depicted here on this slide, and using them to understand the temporal variability of, let's say, macroscopic variables related to the raindrop size distribution, notably the rain rate, as you can see in the lower half of this panel. And of course, a question that one can ask is how variable are these raindrop size distributions in time, but also in space, and what are the important controls on that variability? Now, a raindrop size distribution, as you all know, is nothing else but the product of a raindrop concentration and a probability density function of raindrop sizes in a particular control volume, which can obviously also be written in dimensionless form as follows. So if you would express the raindrop size distribution divided by the concentration on the vertical axis, and you would express it as a function of the raindrop diameter divided by some characteristic diameter, you would retrieve, in a sense, a dimensionless form of the PDF. Now, rainfall rate depends on the drop size distribution, obviously. It's basically the product of the volumes of the particles times their fall speeds times the numbers, obviously, of the drops present in that particular volume. And for the raindrop terminal fall velocity, all kinds of theoretical laws have been proposed in the literature, which I give two here. And looking outside right now and hearing the wind blowing around the Faculty of Civil Engineering here in Delft, I know that these raindrop terminal fall velocities in still air are only a very crude first order approximation to the actual fall speeds. Now, not only does rain rate depend on the raindrop size distribution, the raindrop size distribution also depends on the rain rate, as has been shown by Marshall and Palmer in 1948 and many researchers ever since. So what we're going to look at today is basically how the drop size distribution varies as a function of rain rate and how we can parameterize that. Now, obviously, Marshall and Palmer employed the negative exponential law with a fixed parameter n0 and a variable mean drop size depending on the rain rate. And several other parameterizations have been presented since Marshall and Palmer, notably the gamma form by Ulbrich, and more recently a Bessel law proposed by Villermo and Bossa. Now, we can also relax the assumption of a constant n0 because that has been shown in the literature that is kind of a limiting assumption. And we could do that by introducing a power law relation between n0 and the rainfall rate with parameters k, kappa, and alpha. Now, if you do that, and you also assume that the mean diameter scales as a power law with the rainfall rate, as Marshall and Palmer showed in 48, and many people have shown later, then basically self-consistency demands that alpha and beta are related to each other in the following fashion. And interestingly, this same parameterization was proposed and derived in a slightly different manner some 30 years ago by Semper Torres and colleagues in a slightly different form, as shown here on the right-hand side of this slide. But I'm not going to go into details for the sake of time. But as you can see, the self-consistency constraint on alpha and beta is exactly the same as the one I showed on the previous slide. Now, we can, of course, ask the question, to what extent is this scaling law formalism a good summary of variations of the raindrop size distribution as a function of rain rate? And an interesting perspective on that was presented a couple of years ago in this paper by Villermo and Bossa, who basically proposed that the entire spectrum of raindrop sizes could be explained by the fragmentation of single raindrops rather than by the interactions of raindrops which would coalesce and break up. And interestingly, their parameterization based on first principles also assumed a constant value of n0, just like Marshall and Palmer assumed some 70 years ago. So the question is, to what extent is their proposed mechanism of the breakup of a single raindrop, as shown here on this slide, a good parameterization of raindrop size distributions observed in practice? And to basically test that, we took a couple of spectra published in the literature to see whether that scaling holds or does not hold. So basically, the raindrop size spectra we used here are shown on the left-hand side, taken from a 1943 paper by Laws and Parsons. And we basically applied the scaling law formalism. So we normalized the diameter axis on the horizontal x-axis, and we normalized the raindrop concentration axis on the y-axis. And indeed, all the variability is collapsing onto one single raindrop size distribution with a dependency of n0 with as a function of r according to a power law, as shown on the upper right-hand side. And the average diameter also exhibiting that power law behavior as a function of the rain rate, as shown on the lower left-hand side. So basically, This, you could say, is a confirmation of that scaling law for the raindrop size distribution with values of alpha and beta that are both different from 0. So not consistent with the Marshall and Palmer law, and therefore not consistent with the single drop fragmentation hypothesis either. Secondly, we took the raindrop size distributions from Marshall and Palmer themselves as a function of rain rate. Again, applied the same scaling law formalism, and again, all raindrop size spectra collapsed onto one single raindrop size distribution. Again, an exponential raindrop size distribution. In this case, obviously with a N0 that is constant, independent of rain rate, hence alpha equal to 0. And a mean diameter that scales again as a function of rain rate, which gives us beta equal to 1 divided by 4 plus gamma, where gamma is the exponent of the relationship between the terminal fall velocity and the raindrop diameter. Now, a third and final example are the video observations of raindrop size spectra collected by Mueller in the early 60s, which shows an entirely different limiting case, namely the case where the mean diameter, as you can see on the lower left-hand side of this graph, is essentially constant as a function of rain rate, and all variability of the raindrop size distribution is caused by changes in the raindrop concentration, as you can see in the upper left, the upper right-hand side of this graph. So again, you see that in terms of the scaled raindrop size distribution, the negative exponential form is a very good summary. But in this case, alpha and beta take on very different values, with, in this case, alpha being 1 and beta approximately 0. Now we can summarize all of that on a single plot of alpha versus beta, where the black line indicates the self-consistency constraint between alpha and beta, following from basically the dependence of the raindrop size distribution as a function of rain rate on the one hand, and the dependence of rainfall intensity as a function of the raindrop size distribution on the other hand. And the values of alpha and beta basically identify different modes of rainfall variability, where values of alpha equal to 1 and beta equal to 0, corresponding to the lower right-hand side of this graph, corresponding to what I call a number control, where all variations are caused by variations in the raindrop concentration, essentially. And dots or locations on the upper left-hand side of this graph are basically corresponding to size control, where all variations in the raindrop size distribution are basically mediated by variations in the diameters, and essentially the concentrations are constant as a function of space and time. And as you can see, different raindrop size distributions collected in different parts of the world basically are falling on different positions on this diagonal, and hence correspond to different modes of variability. So summarizing these findings, we basically find that expressing the drop size distribution and its variability in the form of this scaling law provides an elegant framework for analyzing the space-time variability of raindrop size spectra. Secondly, we find a confirmation of the scaling law for a variety of climatic settings and different types of dystromatic devices, where the exponential distribution provides a very good first guess for the shape of the scaled raindrop size distribution. It appears to be that spontaneous raindrop fragmentation as a proposed scenario is closely related to Marshall-Palmer rainfall. And the exponents of the scaling law reflect controls on the space-time variability of raindrop size spectra, from size control to number control. And with that, I would like to close, not before showing you this project in which we're involved, where we're collecting together with colleagues in Switzerland and other places, basically a global database of raindrop size distributions, because it appears to us that many different laboratories and research groups and institutes have collected raindrop size measurements over the past years and decades, but there's actually not a central database bringing all of those together, whereas that would be really interesting, not just for the subject of this particular research project, but for the purpose of, let's say, environmental sciences in general. And with that, I would like to thank you very much for your attention and would be happy to answer any questions you may have. Thank you.
Okay. Thank you very much, Remco. We have time for 1 or 2 questions. Yes, Nan Yu, maybe I'm not pronouncing correctly.
Yeah, can you hear me?
Yes.
Yeah, thanks, Remco. Nice to see you again. So that's a very interesting presentation. I just have one question in the high resolution context. So you showed the alpha and the beta, very good relationship as a function of different rain types of the precipitations. So what do you think the scale of this stability of this relationship? That means, do you expect at very 1 kilometer, for example, at 1 kilometer, the alpha beta relationship will be stable, or at 5 or 10 kilometers, this relationship will be stable? What scale you expect for the stability of the alpha and the beta in the scale, in the spatial scale and the temporal scale? Thank you.
Yeah, thank you very much, Nan. Good to see you again as well, and thanks for your interesting question. I think that is exactly the right question to ask, and we have done some preliminary investigations to basically see to what extent the values of these scaling exponents are systematically dependent on the scale of observation, both in space and in time. But we have not come up with, let's say, conclusive results on that aspect yet. I believe the current project, as Lipen Wang and Auguste Gier are just starting, could shed some interesting perspectives on that. And I think it's a very pertinent, very important question, obviously, because the types of applications we have in mind are obviously radar observations of precipitation, where, as you know very well, typical scales of observation are of the order of, let's say, a cubic kilometer aloft, whereas the typical scale of application, particularly in urban settings, might be the street level scale that Auguste Gier was also referring to earlier on in the presentation today, of the order of maybe 10 meters or so spatially. So that scale transition from, let's say, the cubic kilometer to, let's say, the cubic meter is definitely a very interesting one to investigate systematically. And I hope that Lipen and Auguste will shed some additional light on that in the years to come, and their PhD students, obviously. So thank you very much. No conclusive answer, unfortunately, but to be investigated.
Okay, thank you. So maybe we'll move on to the next part. I just shared my screen with the the schedule. So the next speaker will be Alan Seed. Are you here, Alan? Because I don't see you in the list. I'm not sure you are really here. So in any case, I suggest that we just make a short break, 2-3 minutes, just to stretch the legs if you need to. And if Alan is not here, we'll move on to the presentation by Chandra, just in 2 minutes. Okay. I guess we will be able to shortly start again. Chandra, is it okay if you speak now? You have to unmute yourself so that we can hear you.
No, I was making a joke. Maybe Alan thinks it's a break now because there is a break on the schedule.
Yeah, yes, but the point is he's not connected, so I'm.
Oh, okay.
I don't see him connected, so.
No worries. And let me share my screen and.
I will stop sharing mine, maybe.
Can you see my screen now?
Yes.
Well, let me know when I can get started. And
Yes, but you can start. So we'll now have a presentation by Chandra from Colorado State University with an inspiring title called From Raindrops to Flood, the Role of Dual Polarization Radars in Unraveling the Microphysics of Rainfall. So the floor is yours for roughly 15 minutes.
okay, I went to full screen mode. Can you see that?
Yes.
Okay, so it's nice to follow Remco because he has set up all the physics. And in fact, I had a bunch of normalized distribution slides that I took out yesterday, thinking that Remco would cover that. So I am a fan of the topic. So I'm sure you all know that my area of specialization is radars, and then I've been using dual pole radars to unravel microphysics, and I'm going to invoke Mr. Zawadzki, who is no more, and then he told me, Chandra, you should keep pursuing this because apart from all the large volumes, he said things like rain gauges, disdrometers accumulate rainfall over time, and whereas radar is the only thing that instantaneously captures the DSD. So with that introduction, I have 101 dual polarization here. This is, we just stumbled upon this some years ago. So we started looking at dual polarization signals. It's fundamentally two polarizations, and then they started giving different signals, and then that led to the development of all the dual polarization work. I've been fortunate to be part of the development from the beginning, and so we will go there. So this is the raindrops that made us this topic very important. Originally, dual polarization was introduced to chase raindrops, and I used to make joke to people. I'm in a whole group of hydrologists, so I have to be and physicists. I have to be careful. I'm, after all, an engineer, which is in this community a second-grade discipline. But raindrop is the only body that has its own shape. All other shape of water is by the container the water sits in. So raindrops fall with their terminal fall velocity, and then and with size, it does strange things as it interacts with the environment, and then we start detecting those strange things with the radar, and then that gives rise to chasing the microphysics with this is physics 101. So in my early career, I've been in the business of actually measuring free falling raindrops and measuring their pictures, and then depending on which part of the world you are come from, and I used to tell a lot of my Asian friends that the raindrops start taking the shapes of dim sum, and in West we call it M&Ms and so on. It's a hard sell because a lot of people believe the raindrops are tear-shaped. And I spent a lot of time flying in aircraft trying to measure raindrop shapes. So coming back in the early days, people have proposed simple equations to describe shape of raindrops. So I will skip this. And then Prupakar and Beard proposed a very simple model, just fitting a straight line. It's always easy then compared to all the previous equations. Essentially telling raindrops get more oblate as the size gets bigger. That's the fundamental basis for estimating raindrop shape, and then the size that gets into microphysics. So this is a cartoon of the raindrop shape with various sizes. And you can see very small drops are spherical, almost spherical, but then even if it's slightly non-spherical, even if it's very small drizzle, there is a myth that if it's light rain, you cannot detect a dual polarization radar. And then in fact, I have shown with the famous D3R radar, which operates at higher frequencies at KU, where you can estimate light rain much more accurately than other techniques when you just go up in frequency. Anyway, so as I said, in the 80s, I was busy flying around in airplanes proving the raindrops are not spherical or tear-shaped. And this is some of the first free falling measurement of raindrops shapes. And rest of them is theory or wind tunnel-based measurements. I'll keep going. So the next thing is, which makes it very interesting in terms of contribution to the microphysics of drop size distribution. We studied this. So I don't know if you can see me when I'm on full screen mode. If you can see my hand, I'm waving. Yeah. So raindrops go through oscillations as the big drops hit with small drops, and then they result in the breakup. And then those oscillation modes are actually measurable. And then I actually looked at the mean raindrop shapes, and then with respect to their oblate and prolate, like oscillations like this, and then they have transverse oscillations. And now let's get to gamma DSD's air model, but Remco talked a lot about. I converted to this religion a long time ago. That is, take the raindrop shape distribution and multiply by a concentration, and then rest of the size, just change it into a size distribution. And then once you do that, for somebody like me who's come from a background in statistics, it's easy to follow this as opposed to a model like this in the past. Because once you went away from an exponential distribution, the dimension of this N0 kept changing. That kept bothering me. So I switched to this religion a long time ago. So then I will go through this a little faster because Remco has gone through all the virtues of drop size distribution. But how do we measure this? So we start parameterizing some of these things, and these are, while I have written in terms of the general drop size distributions, you can parameterize it in terms of distribution-free quantities such as drop median diameter, that is half the volume of water is below that and half the volume is above. And then this is, I think Remco showed similar pictures like this. And this is the raindrop size distribution measured on the ground. I'm glad Remco showed pictures like from Gene Mueller from the 60s, because he used to talk to me, and those measurements were made actually to study the impact of raindrops on high-speed bullets or missiles. Anyway, whereas you can also measure these aloft, and then there is a little bit of vertical resolution study, and those are things that can be observed by radars. So here's some paper we published a long time ago where we took raindrop size distributions and then plotted this normalized intercept, which is the NW, and then versus DM. And then DM is drop median diameter. And I am also now becoming a fan of normalizing this with respect to its own mean. However, we started seeing that when you go between convective and stratiform, these change into different clusters. So there is something going on, which I think the other DSD scientists are sorting this out. And this is all derived from, many of these are derived from radar and some from dysdrometer from the ground. I'm going to skip this. This is a lot of electromagnetic equations, how the dual polarization measurements get formed. Let me keep going with this, and then Okay, so a lot of the hydrology community wants to work with rainfall, which is in addition to drop size distribution, it's also influenced by the fall velocity. So I tried to throw some information on throwing DM, which is the drop median diameter, how it traverses for same rainfall. But this is the basic equation that is drop median diameter as a function of differential reflectivity. And you can see that it just works very well. Let me skip this. Okay, here's a very important factor that a lot of the rainfall observations these days is made with the KDP, which is differential propagation phase. And that's a beautiful quantity that scales, its sensitivity scales directly with frequency. So when we want to study this microphysics in light rain, then like I mentioned to you that I use D3R to sort this out, the microphysics for light rain. You can see it's got triple the sensitivity when you go to KU band, which is, this is X band. So this is actually one of the physical bases why X bands are becoming very widely popular for short range citywide deployment for measuring rainfall, and they're doing it very accurately. So that's the physical basis of that. So this is empirical fits of how to get this drop median diameter just purely from ZDR. These are S-band equations. That is a lot of the Weather Service radars in the US are, and also a lot of the French radars, but the rest of the world, they start using C-band. So what I want to do is, let me skip all this, and then this again is the same equation. And I cut a lot of the slides as I was watching Remco so that I'm not repeating, but I think that's about, okay. Let's, this is the interesting thing that I invoked Zawadzki. So let's say on the ground, I don't know if you can see my mouse as I'm moving it.
Yes, it's possible.
This is data from chill, and this is convection, and then this is stratiform. So sometimes, and I haven't plotted the Doppler here, and then we can see this is function of time. So within the same storm, this is a long storm, as you can see, it runs about 70 kilometers. And if you put a disdrometer here, it's going to be, and obviously you need to make those measurements at 1 minute resolution because of all the Doppler that happens here, the drop size distribution you measure here is going to be unraveled by rapid change. Whereas if you are in this portion, it's steady, and then you can measure this carefully. So this is this type of picture is what, and this is the stratiform echo, and this is convective echo. And since our colleague from Dr. Wang talked about vertical resolution, so I just threw this picture in to show a lot of variability in the vertical. But as far as rain is concerned, we look at all the variability in places like Colorado where the ground is very high, the variability below 2.5 kilometers in the summer, whereas some other locations, it's about below 4 kilometers. That's all the rain variability. And with that, I would say the end. That's, I will leave the eye candy picture up. Did I stay within 15 minutes?
Yeah, perfect. Thanks a lot for your presentation. So we have time for a few questions.
Sorry, I have a question. Actually, I found it very interesting, especially the plot you're showing. You try to justify why X-band radar actually at 3 gigahertz that's linear approximation. But I don't fully get that plot. Would you mind explain a bit more about that one?
Okay, this is a little cleaner plot. So this is KDP. You see it's normalized with respect to water content. And you measure the same rain. Let's say you had 2 radars, one measuring at S band at 3 gigahertz, and another one measuring at X band. This KDP is right now the workhorse of a lot of the rainfall estimation. And for the same raindrop size distribution, actually, I have simultaneously measured this same rain event with 2 different radars. And so you will see that the KDP at X band, it's actually 3 times higher than the KDP at, so it's very highly sensitive. So you will get much more accurate measurements because KDP is measured over a path. So you have to let the electromagnetic waves propagate. So you will get higher accuracy rainfall rates. And also X bands are normally deployed at short ranges with 30-40 kilometer distance over urban regions. So that practically makes the resolution volume smaller just because of how we use it. And so as a result, people get fairly accurate rainfalls. In fact, I can tell you some example. We have in the city of Dallas-Fort Worth, I don't know if you have time for a story. They deployed X-band radars and then compared it with gauges. And then it turned out that the gauge rainfall didn't agree with radar. So then after some time, they asked me to come and check something. I tore the radar upside down and I couldn't find anything wrong to change anything. Because KDP is a quantity that's independent of calibration. And I said, sorry, my radar is still showing the same thing. Then they said, oh, don't worry. We will take the ground measurements and then change all the radar rainfall estimates to match the ground and then move on. I was not happy with that because let's say, for example, you're making a mistake in ground measurements, which is made at one point. Then you take it and translate it to the radar. What it means is you're taking the mistake made at one point and converting it to a huge area. You're amplifying your mistake. At that time, somebody from the crowd saw me that I was low. Of course, they were the hosts, so I can't complain. To make a long story short, imagine just next county, they said, talk to those people's rain gauges. They are well maintained. So it turns out when I went to the next county, it was smack on. So the bottom line is then when they did further investigation, they found that some of the gauges that they were using was not well maintained. There was tree had grown over, and then some of them had not been functioning, but people had been blindly using the data. So the whole thing has been flipped now. When there is a large disagreement between radar and gauges, they send technicians to go check the gauges now instead of the other way. So that much reliability has come to X-band and higher frequencies now, especially if you're using it over short ranges, over urban regions. Sorry, that's a long story. I'm at least entertaining you.
No, but it's really encouraging to see that.
Yeah.
I have one question because you talked about the variability and the variability of the DSD in space. And according to you, how should it be accounted for in radar measurement, and especially the one that is occurring below radar gate scale?
So take, for example, this one. So I have had other plots. You can have you can measure differential reflectivity, and then you can actually make a spatial map of drop median diameter here, and then make a plot of that. And then I have done that in the past with other things, and then to see how the nature of raindrop size distribution itself changes. And this is captured almost instantaneously. Of course, you have to realize this is within the error bounds of conversion equations from raindrop size distributions to radar measurements. So if you do this, we can actually get radar-based DSD maps. We have produced in the past maps of drop median diameter as a function of time. And then you can also watch the vertical evolution of drop sizes. And we can watch things like when you're in the coastal regions, continental storms versus oceanic storms, that difference will be in your face. You can see that the median drop size diameter will be much smaller when they come from oceanic events as opposed to continental events, because the continental storms have an ice core in them that holds the raindrops from breaking up too much, whereas they are made up of a lot of small drops. So that's why a lot of the tropical events, they don't produce very high reflectivity, but they produce a lot of rain because the drop median diameters are smaller. Did I answer your question, or what? Talk all over the place?
No. It was partially answered, but I was also mentioning the variability of DSD occurring within a radar gate and how it affects the measurement itself.
Yeah. So if we can, yeah, anyway, we don't have to solve the problem in this call, but
No, for
we
sure.
can continue working on this.
Okay. Thank you. We have time if there is one other question. Someone in the audience, just raise your hand numerically. Yes, Nan, you have a question?
Please.
Please go ahead.
Okay, so again, thanks for the presentation, very interesting. I think for the relationship, you said that the KDP divided by the W, and we get very good relationship with the ZDR or the mean diameter. This relationship shows that X-band radar is very better. To say that, yeah, I fully agree with that. I just have one question about that, is that you showed also at the beginning of the presentation, we have the different shape of the drop shapes as a function of the diameter, and you showed that we have some variability of in this relationship. So what do you think? Do you think the KDP divided by the W as function of the ZDR? Do you think this relationship, there is some sensibility to the shape of this shape of the drops? That means if we
yeah, so that's a very good question. So eventually, what all these this is all microphysics. Of course, we with radar doesn't see individual raindrop shape oscillation. So one of the things I tried to show was, if I have to go to my earlier pictures, and yeah, if you see this, do you see I changed my slide?
Yes, we can see it.
So I did go measure this in Florida, and High Plains is Colorado, and this will manifest itself as a different shape size relationship, which will manifest itself as into a parametric rainfall equation, and with KDP. So, and it's not widely varying. It does change a little bit, because if you see, if most of the raindrops are in the 2 millimeter range, it'll be more focused on this type of access ratios. Whereas if they are big raindrops, then it'll be a little different. So when you use KDP and ZDR, so ZDR will tell you which part of the region you're operating, and the KDP will tell you the absolute concentration. So there are things that you can tune out and try to make this more robust. But you have to be careful when you throw more measurements. Measurements come with their own errors. I mean, I'm talking about actual measurement errors, not physics errors. Physics errors, we have a solemn duty to fix. But so we have to be careful when we throw a second measurement. The improvement brought by the second measurement due to improved unraveled microphysics is important enough to overcome its own measurement errors. And when we do that, so there's a lot of work going on in that area. But so far, for large applications, these things get determined zonally. So we do a few experiments over time, and then I'm a big fan of simplicity. For again, if you're doing research to publish papers in Nature, then we have to get into all these topics. Whereas if you're just producing rainfall that the people can use, whether to take as input to the flood model and stream flow and all that stuff, then a simple KDP based relationship is good enough. So it depends on the application. Did I answer your question?
Yes, thanks very much.
Okay, so thank you very much. So now, thanks a lot, Chandra, especially for waking up quite early to be here.
No worries.
So we can move on to the next presenter, who will be Daniel Scherzer from HM&Co ENPC, with a presentation entitled Beyond Scalar Modeling of Multifractal Precipitation and Wind Field. So Daniel, you can share your screen.
I hope I will succeed.
Yeah. So we can hear you well.
Yeah, but I don't see my application. Screen, window. Okay, I will try something else. Wow. I can get the screen, that's all. You see something?
Yes, we can see the whole screen.
The whole screen, yeah. I'm not able to do the... Okay, I will put... I will do something a bit strange. Oh, what is it?
Are you sure you opened the correct presentation?
No. Yeah, it was correct. Not correct.
There is one behind.
Yeah, this is a PDF. I will use the PDF, I think. Okay, it's not very good. Okay, it's more or less acceptable?
Yes.
Okay. So the talk would be quite different from other talks, I believe, but nevertheless aiming to solve the same problem, to have better modeling for the precipitation and wind field. Okay. I hope you got the second picture, the
yes.
second slide.
Yes, we can see the second slide.
Okay, unfortunately, there is no motion because on the right-hand side, there is a complex motion of multicellular rain field, starting with small cells which cluster together to form at the end a front. Okay, a kind of situation that many of you have already experimented. On the left-hand side, there is something else, which is not exactly a scientific object, but an art piece called Windswept, which has been developed by Charles Sowers at the Exploratorium of San Francisco in order to show that the complexity of the wind field, especially on the surface, from time to time you have a laminar flow and suddenly transition to turbulent flow. Okay, you are all experimented about that. So just a kind of recall. Okay, the difficulty behind that is, of course, that the motion is principally defined by the Navier-Stokes equation, and there is a basic problem with Navier-Stokes equation. We are still unable to demonstrate the existence and uniqueness of solution, and that's related to the fact that the Navier-Stokes equations are strongly nonlinear. You have an advective term, u grad u, which is quadratic, and that's the source of the difficulty. But independently of this difficulty, this fundamental difficulty, you have simple symmetry, scale symmetry. That means if you are dividing the location x by arbitrary scalar number lambda, then you can renormalize all the other variables like time, t, and the velocity, and so on, by lambda to the power of something, and you can get at the end the same equation. There is a unique parameter defining what is going on for the Navier-Stokes equation is gamma, and this last exponent can be defined if you are making a new hypothesis as done by Kolmogorov in 1941, that is the flux of energy is more or less constant, homogeneous. In that case, you obtain a unique exponent gamma, which is one term, corresponding to the well-known spectrum of Kolmogorov with the exponent 5/3. In fact, this special solution has been a little bit abandoned in favor of the fact that there is a whole spectrum of gamma values, and they are distributed according to the probability distribution, which is indicated here. Okay, so the interest of this consideration of symmetries, the scale symmetry, it simplifies a lot the complexity of Navier-Stokes equation. And this can be used for practical questions, including the problem of scalar Rein rate. It was first clarified that Rein rate, which is usually considered as the flux of water going down to through a horizontal surface, was singular, and this is better explained with the help of multifractal, which shows that in fact it could be a mathematical measure, a singular mathematical measure, and not a function, and in fact rather a flux across scale. This has been used a lot to make different studies and to have a coherent framework with the singular behavior of the Rein rate. But nevertheless, it was done with the Rein rate, the flux of water going through scale, but only along the vertical. At the same time, we are speaking about advection and so on, so it's a bit limited. So there is a new step to be done to see the flux of water across scale, not only along the vertical, but in the different direction. Immediately, that means we have to consider cascade process, which are no more scalar valued, but which has multiple components, or it can be called multivariate. Or it could be said that the multifractals are vector valued instead of being scalar. It could be even more general than that. In fact, the generic solution combines three components. The first one is anisotropy, because indeed the vertical is very specific, spatial, and either for drops of water, but also for the dynamics. And you need also robust statistics that's generated by Levy stable processes. And the new thing now, when we are considering a multi-component, multivariate cascade, is the fact that there is a problem of commutation on anti-commutation of different operators. That's new thing. Sorry. I will first just point out that this question of scaling anisotropy along the vertical has been explored a lot for different questions, including for the dynamics. The general idea is to get rid of the usual isotropic metrics in favor of, which can be defined by self-similar sphere in favor of anisotropic matrix like this one, which is defined by self-affine ellipsoid or ellipsis if you are taking a vertical cut. This has a lot of consequences I will not develop, but for example, for the vorticity equation, there are new ways of understanding the fact that some of the interactions are extremely weak, some others are extremely strong. Okay. Now, I just want to play a little bit with the problem of symmetries of vectors, and starting with the basic question, do you have some operators which are roots of the unity? The answer is none in 2D. Sorry, I have a problem with, okay. Okay, yeah. Okay. What is well known is, for example, the rotation, which have the properties that the rotation of angle pi over 2, when you are iterating it twice, you obtain an anti-symmetric of the initial position. You are starting from x0 to x1 to x2, which is simply equal to minus x0. That means that I square is equal to -1. Okay, this is very classical. What is less classical is the fact you have also to deal with mirror symmetries across a plane or an axis, which is figured on the right-hand side of this slide. And this is, there are two of them which are presented here, J and K. J is a mirror symmetry across the main bisectrice, and K is equivalent mirror symmetry along the horizontal axis. The new property now is that their square is equal to 1, so they are really symmetries of the unit root. Now you can, the question which is solved for rotation is that you can look for elementary deformation which lead to a rotation of angle pi over 2. It's simply a rotation of epsilon time pi over 2, and that after that you can iterate a given number of times and you obtain I again. You can wonder what would happen, what can you obtain the same for J and K. This is not trivial. You can wonder what to do, and in fact the answer is a bit surprising. It's in fact you obtain hyperbolic trajectory from the position x0 to x1 or to the position x2. So that's a bit, you are leaving the spherical geometry to hyperbolic geometry, which is a bit unusual and from time to time very surprising. Now you can combine these different symmetries with to obtain by simply a linear development with respect to this kind of basis of operator, and this is illustrated here with what is called pseudo-quaternion algebra, which is just the 2D linear algebra, and you can see that you have a very simple relationship between the different basic components that commutator of J and K produce I, and so on. And on the contrary, the anti-commutator are all 0. You obtain a basic relationship which is I square equal minus G square minus K square equal -1, which was already obtained. And most surprising is equal to IJK. This is kind of almost standard relationships which are obtained for what is often called pseudo or split quaternion. In fact, they remind a lot the quaternion equation of Hamilton, which was derived in 1843, and which is just written down here. I squared equals j square equals k square equal the product of the three of them and equal -1. In fact, the relationship between the two is given here. So there are different games you can play with this kind of algebra, which are very simple. Okay, what is very systematic is what is called Clifford algebra, which have dimension 2 to the power n, where n equals from 0 to infinity, and which represent, for example, the complex number for n equal 1, quaternion, the usual quaternion for n equal 2, and also hypercomplex number for n larger than 2. What is very important is, in fact, you are able to have a quadratic form Q for the signature PQ of your algebra, and which has part of it with units of the root of the +1, and on the contrary, roots of -1. And there are a lot of games you can play with them. As soon as you have an algebra of generators, you can form a group by exponentiation, and then after that you can ask whether you can obtain a stochastic Clifford algebra with some robustness, and this is indeed done with considering Levy stable vectors. Their generic properties simply they are stable under renormalization and recentering by when you are summing n of them. And in fact, they have a stronger property like the Gaussian variable is that they are attractive for any distribution y having the same type of tail, and once again being renormalized and recentered by the coefficient Bn on In. Okay, this is usually done for real variable, but it can be done by vector. There is a small subtlety, not so small, but subtlety is that sometimes Bn is considered as just a vector, and N, on the contrary, as a number, as a scalar. Whereas, in fact, the full generality is obtained with the N is being a matrix. Okay. I will just mention that as soon as you have this kind of algebra, you have a bilinear form which allow you to define a Laplace Clifford transform, which give you again the characteristic function that you are looking for. So it's a cumulative generating function, but this time for operators instead of scalars. So you are able to extend what we already knew about the scalar processes, scalar value processes to vector operator valued processes. And then you can apply these operator processes to transform a field by a cascade process to much smaller scale. There is a big difficulty is as soon as you are playing with Levy generators, you can have divergence of moments, and you have to be careful to play with given subset of value of Q, where it's you obtain finite values of the characteristic function. Okay, just now.
Well, if you have 1 or 2 minutes left to allow time for a few questions, Daniel.
as soon as you have done that, you can play the game either in dimension 2 or higher dimension 2 to the power n of generating from a homogeneous vector field a very complex field. Unfortunately, the PDF file cannot show it. This is done first for a 2D field, and this is after that done for 4D field. So it's a 3D cut of a 4D field obtained with quaternion algebra. Conclusion is the fact that we are able to extend what we have learned about scalar representation of cascade, and therefore to handle intermittent field with vector values. We are no longer limited to scalar valued field. This is obtained by multifractal operators and an explanation from a stochastic Lie algebra of generator. And I pointed out some of them which are already well defined. And you obtain a group of transformation to obtain the field at different resolution. In fact, you are going from a field of physics of field to singularity field physics, and no more with a dependence on scale. And I believe that this kind of approach should be tested within the project in comparison with other approaches which have been already presented. I finish. I'm sorry for my voice and also the fact I was not able to display the presentation.
Okay, thank you, Daniel. So we have time for a few questions. So just raise your hand numerically. Okay, so maybe I will just ask one short question, waiting for other questions. You mentioned in the conclusion quite a lot rain rate, but what can you say about wind fields, which are also of interest in the project, notably with regard to the wind drift effect?
But in fact, it was indicated very quickly somewhere that we are no longer to look at the rain rate along the vertical, but along different direction, and that corresponds to the, for example, to a horizontal drift. So in fact, we need to do a kind of acknowledgement of a paradigm shift we have been more or less doing from considering a rain rate field only being defined in one direction, that is along the vertical, that is also horizontal maps, to a vector field having different direction, not only the vertical one.
Okay. I don't know if there are other questions. No. Okay, but then
sorry,
yes, Lipen.
so quick one is how in our observation how can we apply this new instead of a scalar and then it's more like a vector, this new framework to our observation? Okay, more specifically, it's our observation, for example, from distrometer or from our observation, it's enough to really test this theory. Yeah.
Well, again, you are in fact more and more led to consider a vector field of rain rate, but it's done in a schizophrenic manner in given way for the present time. We are looking along the vertical, and on the other hand, we are saying, yes, but there is a horizontal drift. In fact, the reality is not that. We have motion along a lot of different directions, even if the main one is vertical. So we have to deal with this new approach in given way, but which is just a recognition of what we are partially doing now. But we are doing it partially instead of doing it fully and being fully conscious of what we are doing. After that, you have really no time to show that some of the favorite tools which have been developed to measure the parameters of scalar multifractal field can be extended to multifractal, multivariate fields. But this can be done. Of course, it's much more demanding, but this is not impossible.
Good, thank you.
Okay. Thank you. Then we are approaching the end of the meeting, so I would just like to thank all speakers for their presentation and all of you for attending. And we are really looking forward to exchanging with you either online or in person at conferences. And we will put some information about this meeting on the project's webpage soon. Voilà, so thank you all for attending or presenting.
Thank you.
Thank you.
Thank you. Goodbye.
Thanks. Bye-bye.
Bye.
Thanks.
Bye.
Bye-bye.